Okay, so this AP review for AP Physics 2 is going to be about buoyancy and hydraulics. So, AP2, oh, if I could spell, buoyancy and hydraulics. I mean, I spelled it right, but it always looks wrong when I write buoyancy. So, key facts. Big picture facts. Number 1, the force buoyant depends only on the fluid volume, fluid density, and gravity. Okay? Gravity, fluid density, fluid volume. So if you change something about the object, unless you change the object's volume, the buoyant force doesn't depend on any of the other changes you make. You put it on Mercury where there's a ton of a lack of atmospheric pressure, buoyant force doesn't change. You put it at the bottom of the ocean where the pressure would crush a human being, buoyant force doesn't change. The only thing that matters is the volume, the density, and the gravity acting. So that's the first big picture piece. The second piece is volume of object in fluid equals volume of fluid moved. So, the volume of the object equals the volume of the fluid, let me say it like this. This is probably the better way to say that. The submersed volume of the object is equal to the volume of the displaced fluid. Okay? So submerged or submersed volume of the object is equal to the volume of the displaced fluid. So if an object displaces more fluid than it takes up, go back to that idea from the last one, an object that floats displaces its weight. An object that sinks displaces its volume. In this case, an object that is submerged always has the same volume. The part that is submerged is the same volume as the fluid that we're going to use to find the buoyant force. Okay, so that's the second big key. And then the third big key for buoyancy specifically is this. Where was I going with this? Sorry, just completely lost my train of thought. So when we're doing with submerged objects, remember that if you're all the way sunken, it's your whole volume, okay? But if you're floating, it's only part of the volume of the object. And then when we're working with the hydraulics part, what we have to remember is that force on one part of a fluid, so Pascal's principle is the last big one here. Pascal's principle, or Pascal's law, is that the force buoyant, this one is usually given as an equation, force buoyant is equal to the density times the volume of the fluid times gravity. So make sure that when you do these two pieces, they only come from the fluid. Now the volume will be the same as the volume of the object that's underwater, but it will not have the same density. Okay? So force buoyant is going to be a force just like all the other ones, and it comes about, The reason we have a buoyant force, so last piece, the reason for the buoyant force is that pressure changes with depth. So what does that mean to us? That means that the bottom of the object experiences more force up if I could write. Sorry guys, I'm really better than this. More force up than the top of the object is pushed down. So what we've got is this piece comes due to the gauge pressures. The gauge pressures, pressure at the top is less than pressure at the bottom. So the gauge pressure at the bottom of an object will be larger. The fluid will push the object up more on its bottom than the top of the object's fluid will push down on the top of the object. And that's kind of weird, but that's what really is happening here. So when you're at different levels in a fluid, because of what we talked about last time, the deeper you go into a fluid, the more pressure you have experienced, or the more the object experiences the pressure, because pressure on a particular layer gets pushed out in all directions. So the force buoyant is going to be a smaller number on top than it is on bottom, which is going to give me a net force upwards. So that's where the buoyant force comes from. So let's talk about that a little bit, and then we'll come back and talk about the hydraulics piece. So let's do a couple of buoyancy pieces. And once again, I'm going to give you some force buoyant. So let's look at, on the questions to my right, let's look at question number 1. So we have this scenario, and we've got a piece of cork that's being tied to a string at the bottom. Okay? So the cork, they tell us, has a weight. Weight is force due to gravity. Mass times gravity. And its density of the cork is 0.25% of water's density. Okay. So the cork, the string is tied around the cork and attached to the bottom. The cork is totally immersed. So express in terms of the cork weight the tension in the string. Okay, so now we have to remember a tiny bit about forces and free body diagrams from last year. So here's our first piece. What forces do we have? Well, there's force tension that holds it down, and there is force buoyant up, and there is also force due to gravity down. So in essence, I'm going to need my force buoyant. My force buoyant is going to need to be big enough to balance those two. So that if we write our equation, the sum of the forces equals 0. So there's no acceleration. Then we have force tension plus force gravity. Whoops. Let me write the symbols and then I'll fill it in. Force gravity. These are both downward forces, so we're going to give them both negative signs. And then we have force buoyant is going to go up. So force buoyant will be equal to force gravity plus force tension. The buoyant force is going to come from the fluid, the density and the volume and the gravity of the fluid. Okay, so let's start with what we know, and then we'll fill in that piece. Force gravity is mg. Force tension is what I'm trying to solve for, And they tell me that the weight and density, the density of the cork is equal to 1/4 the density of the water. But the volume of the cork and the volume of the water will be exactly the same. Because wherever the cork is displacing its own volume. It's submerged, so it's displacing its own volume of water. So when I go to do the force buoyant is density times volume times gravity. Here's what I get. The density of the water is 1/4 that of the cork, okay? So that's 1/4 of 1. This is density, water's density in grams per centimeter cubed, okay? Then they also tell us that mg, it's just mg, and the force tension is going to be whatever it is. So what we need to figure out is on this side, hang on just a second, on this side we've got to figure out a relationship between the weight of the cork and the weight of the water. So here we go with that. We're going to get this piece right here is density times volume, which is really just mass of water, and then times gravity, which is gravity, it's 10. So what is the mass of the water? Well, if the density, if they have the same volumes, the only thing that can make a difference in the density is the masses. So if the cork is 1/4 of water's, then water's mass would be 4m. So it's 4m because the density of cork is 4 times that of water. So water has a density 4 times as much as the cork. So I fill in 4m. So 4mg equals mg minus force tension. So force tension would need to be 3mg. Another way to work this problem is to think to yourself, okay, so if the cork was above water, only 25% of the cork would actually be underneath the water. So 3/4 of the cork would be outside the water. So I would have 3/4 of the weight would be outside the water. That's another way to think about it. Okay, so now let's look at that's a hydraulics. Okay, let's look at number 10. Look at number 10. Feel free to pause, and I would actually say that the best thing to do is to pause these questions and then wait to hear the explanations, or to work a lot of these questions because the answers are at the end. So on number 10, if you want to pause, go ahead and do so. I'm going to keep going. So we have 50 cubic centimeters of wood floating on water, and 50 centimeters of cubic iron is submerged. So the volumes are the same. Volumes are the same for wood and iron. Okay, so then which has the greatest buoyant force? Well, let's see. If the wood is floating on top, so here's our tank, and the wood is floating on top, and the iron is completely submerged, here's what we do know. They have the same volume. So if we look at the volumes, the volume for one is equal to the volume for the other. But the wood doesn't have all its volume submerged. It only has part of V. And its part of V would be equal to mg. So here's where we're at. The forces on this one would be force gravity down and force buoyant up. These two are exactly the same. But to get the buoyant force to be the same as water's weight, we only need to cover a little bit of the water or the wood with the water. what's happening with the lead? Well, the iron. The iron's whole volume is submerged, which means its whole mass is submerged, so its density doesn't really matter. What does matter is the force buoyant comes from the density of the fluid, the volume of the fluid, and gravity. So for the iron, the density of the fluid is the same, gravity's the same, so here's iron, and if we look at force buoyant on the water, density is going to be lesser, because not all the object is underwater. Excuse me, but let's say it like this. The density of the fluid is the same, but the volume of water will be smaller. So the volume of water is smaller, and gravity is the same. So if you look at the iron, it gets all of its volume. So that tells me that the buoyant force that is applied on iron is some number. But it's not enough to keep the iron afloat, where the buoyant force applied on the wood would have to be a smaller number because you're not getting the whole volume of the wood underneath. So in other words, let's come back to this. If the wood was completely submerged, we would know for sure that they have the same buoyant force. But it takes less water to push the wood up. So because of this difference in volumes, you have a buoyant force on wood that's equal to the weight of the wood, but is less than that for the iron because it's not enough to hold the iron up. So once again, what's the key takeaway? Float means you displace weight. Displace your own weight. Sink, you displace your own volume. And so what we have for block number 1, the wood block, is that its weight of wood, is less than weight of water, and the weight of iron is bigger than the weight of the water because it sinks. So that's how we would work that one out or think through it. Okay. So let's look at number 15, and I'll give you a minute to do that, and I'm going to make another new page so I have some space to work. And we're going to go and do the quick review for the hydraulics. So, copper just barely under the surface. So the copper is completely submerged in case A. This is position 1. Position 2, here's position 2, we're halfway down. And position 3, we're on the bottom of the container of fluid. So we have fluid in here. And they ask me, what is assume that the water's incompressible. Water doesn't compress. You can't smoosh it. What is the ranking of the buoyant forces acting on the copper blocks for these from least to greatest? Well, let's see. The formula for buoyant force is density of the fluid, which is the same for everybody. Volume of the fluid, and in this case, volume of the fluid is equal to volume of the object because we are submerged the whole time. Every position is submerged. So the volume of the fluid and the volume of the object are equal to one another. That's another one that's the same. And gravity is the same for everybody. So that means that the forces, buoyant force 1 has to equal buoyant force 2, has to equal buoyant force 3. Once again, the buoyant force depends on the volume of the fluid and the density of the fluid. It does not depend on the mass or the weight of the object. It does not depend on the pressure. It does not depend on the pressure. It depends on amount of fluid you move, and the density of the fluid and gravity. Okay, so let's see. Let's do one more for number 19. We'll do number 19, and then we're going to stop there on this, and we'll do the... Actually, let's just go ahead and do the hydraulics. I think you've got plenty of ones you can practice out of this, so let's go ahead and just hit the hydraulics. So what's true about hydraulics? Hydraulics also uses Pascal's principle. And what does Pascal's principle state? Well, here's the key. In a closed system of fluids, closed system of fluids, closed tank of fluids, closed container of fluids, the pressure, or excuse me, the force, let's make this capital, the force applied anywhere is equally applied everywhere. Force applied anywhere is equally applied everywhere. So what does that mean? That means if I have a container of fluid, whether it's water, whether it's a gas, whether it's, molten iron, if it's a fluid in here, I have a fluid in here, and I put something on top, even just a small thing in this one little section, that extra weight gets transmitted everywhere in this fluid, and in every direction, actually. So the fluid changes, the overall force on the fluid changes when you add a force. So even if you just push water down with your little finger, that force gets applied and transmitted everywhere in that closed fluid. And so what that leads to is two different things. Number one, Pascal's principle has that each layer of fluid. Actually, let me say more specifically, each horizontal layer of fluid, each horizontal sheet or layer of fluid is at the same pressure at every point on that layer. So if I pick a layer of fluid, here's my thin sheet of fluid, this is my thin layer of fluid, the pressure on every single piece of that paper, every single piece of that sheet of fluid, whether it's gas, liquid, or whatever, is at the same pressure. However, the second part says that deeper depth increases pressure. Depth increases pressure at each level. So, if you go lower in the fluid, if I pick some other layer of fluid, so let's pick another layer of fluid. If I pick a layer of fluid down here, I pick a layer of fluid down here that is below the top level, this one has P2 is going to be greater than P1 because it is a lower depth. So as you move down in a fluid, the depth continuously increases, and that comes about because the gauge pressure, which is density times gravity times height, your depth is continually going up, So the weight of water above you is continually increasing. So that leads us to the idea that we use in hydraulics. And what hydraulics says in general is that pressure at point A has to equal pressure at point B for fluids at the same level. So how do we apply that? Well, I'm going to need a new page. Seem to need that a lot. So a new level means that here's what we're going to use. Hydraulics says we can lift very heavy objects with small forces on small areas. We can lift very heavy objects. Small forces on small areas are transmitted as large forces on large areas. So Pascal's principle is telling us that if I take a closed container, here's a closed container, and it's got a very, very little piston, and then we've got a big old trough down here, and over here I have a huge big piston. So and by piston we mean a floating object. A floating object on top. Here's my piston there, and here's my piston over here. There's my piston. I can push down with a little f here on my little a, and it will get transmitted through the fluid to become a big F on a big A, meaning that pressure 1 equals pressure 2. So little force over little area equals big force over big area. And so that's the whole principle of hydraulics, is that I can only apply small forces. I can't lift a car by myself, but I can push on a small piston, and if I can push the little piston on that small area and get it to move, then I can make the car on the other side move. And so that's what hydraulics is about. So let's look at some hydraulic questions real quick. And we're going to look at, let's see, I don't want to get into that one. Here's one, number 43. Number 43 is like a blood pressure cuff. So we'll do number 43. We've got Y1 and Y2, and it doesn't really matter what fluid's in it. At the bottom of both tanks, the bottom pressure all the way across is the same. So the weight of fluid on the left has to be equal to the weight of fluid on the right. So force, which in this case is weight, force due to gravity, over the area of the circular bottom has to equal the force due to gravity on the right hand side, the weight, over the area. They tell us that the two arms, because of the way they've shown it, the two areas are going to be the same. So the force due to gravity on the left, which in this case would be the weight of the, let's see, water is on the left, okay? So we have the weight of mercury plus weight of water has to be equal to the weight of mercury on the right. So since the areas are the same, that's what the closed container helps do for us. In this case, the two arms are the same area. In the case above, they would not be. So I'd actually have to worry about the areas of both of them as well as the weights on both of them. But in this case, the two areas are shown to be the same. So the force due to gravity of the mercury and water is equal to only mercury on the right. So they ask us some questions. Which of the following is correct? The pressure at Y3 is the same in both arms. Well, the pressure would definitely be the same because they're at the same depth of fluid, okay, or lack of depth of fluid. They're both, in one case, it's weight of water and atmospheric. The other one is just atmospheric. On the second question, the pressure at height Y2 is the same in both arms. Oh, what's happening here? So here's where we got to be careful, and I'll have to apologize. The pressure at height Y3 is not the same in both arms because the fluid of the mercury is under just atmospheric, and Y3 on the left-hand side is atmospheric plus water. So those two weights are not the same, or the two pressures are not the same. Then on the next piece, same thing for number 2, you have a weight of atmospheric pressure plus water, atmospheric pressure plus mercury on the right. The pressure at the bottom of the right arm is greater than the pressure at the bottom of the left arm. That can't be right because the pressure at the bottom is the key here. The pressure all the way across the bottom of the tank has to be stationary, or the mercury and the water would still be moving up and down. So in this case, it's the one at the bottom, letter C, is wrong because it should say they're the same. So now we got to figure out what's going on. The pressure at Y3 is less in the left arm than in the right arm. Well, let's see. The pressure at Y3 is less in the left arm than it is in the right arm. And the pressure at height Y1 is greater than in the left arm than in the right arm. Okay, so what's going on at Y1? At Y1, they are both under atmospheric pressure. So which one of these answers is the correct one? Which one of these answers is the correct one? Well, working your way up, we've got to worry about at Y3, is pressure at Y3 the same as Y1, or is it at Y2 that they're the same? Or is it at, can we make a statement about Y3 compared to Y1? Well, Y1 and Y3 are going to have the same amount of force at those two positions because the weight of the fluids are what balances this. The weight of the fluids is our key piece. So just because they have the same force doesn't mean they have the same area. And in fact, I think, because of the way they've worded the question, you cannot assume these two areas are the same. So I think in my statement of the problem, I used a video, a visual. It looked like they were the same size, so we don't know that part. We don't know that part. We can't assume that part. So we have to figure out where would the pressures be the same. Well, the weight of the fluid on the left, so this weight is exactly equal to this weight. But for this one, it takes us to get to Y1, and this one only takes us to get to a height of Y3. So in Y3, if I stop here on the left-hand tube, I don't have enough weight to balance the weight on the other side. So it looks to me like the correct answer should be letter D. And we're going to then go to a free response question, but I'm going to check this just to make sure that I read everything that they meant us to read on that, and I didn't read anything into it. Okay. Right. So we've got A is wrong, The pressure at the bottom of the tube everywhere is the same, which rules out C. And it also tells us B is right. Did I misread B? Hang on just a second. Let's go back. Because they're asking which one is correct. Which one is correct? Oh, yeah. They're both at the same depth of fluid, so B would be the correct one, because if you're at the bottom of the tank, you have the same pressure, and so forth and so on. So my fault. I misread what B said. So B would be the same, because you are at the same height, and in both cases you have mercury all the way filling the tube. So your forces there, your forces in your areas there, even if they aren't the same force and same area, they will be the same ratio of force to area at both of those places. So B was the correct answer. Okay, so let's look at a free response. We're going to look at this one, and the reason I want to look at this one is because this is a lab question, and I think it's good for us to see how to do a lab question. So we're just going to take a minute to do a lab question here. I'll give you time to read it, so pause your video and do what you need to do. And this is kind of going to involve things from first review and second review. So here we go. We want to determine, the big piece we need to know is determine the density of the fluid. Okay, you're given a spring with a constant, spring constant K, an object of known mass and known density. So we know we have objects and we know mass. We know mass. Its mass and its density. Okay? And you can choose a ruler, a stopwatch, or a string. Explain how you can find the spring constant K. Well, first of all, we're going to do that in air. In air. Hang a mass on the spring. Okay? Find the spring's displacement using a meter stick or ruler. Then, force due to gravity down will be equal to force spring up when it's at rest. So mg equals kx. So k would be mg over x, and you know all those things. To find k, the spring constant. Okay, so there's part A. Now, the spring object system is arranged so that the object, but none of the spring, is immersed in an unknown fluid. Describe any changes that are observed in the system and explain why they occur. Okay, so now what do we have coming into play for part B? The spring scale will read a smaller weight for the object due to the buoyant force up, due to the new buoyancy or buoyant force up. Okay? So, what we have now is force gravity down, and up we have force buoyant and force spring. So now we have an apparent weight it's less than the true. And that comes from the fact that force gravity down did not change. But now you have a buoyant force helping the spring. And so, for example, if the force gravity was 5 newtons and the spring force read 3 newtons, you would know the buoyant force is 2 newtons. Okay? So the spring will not stretch as much because you have a buoyant force now acting on it. Or the fluid itself will support some of the weight of this object. So now how can we find the density of the object? Well, let's see. We know what the buoyant force is. That's what I'm going to say here. We can use the fact that force buoyant is density times volume times gravity for the fluid. The volume of the object equals the volume of the fluid displaced. So force buoyant, which we know will be equal to density, which I don't know, so this is what I'm going to solve for. So I know this value, CB, and I know V, and I know G. This is known and this is known, so the only unknown left is the solve for density. And then they ask you to show the symbols and the measurements. So I think you can handle that from here. And that's a typical lab question. Lab questions will be worth 5 points out of the 12 on their question. And you need to identify what you measure, always what you measure it with, and what formulas or relationships you're going to use to solve the question or answer the question they've asked. So there's a lab question that would be about these things. So that's where I'm going to stop for this video review, and we'll pick up with it on the next lesson. So have a great day, and I'll talk to you guys later.